Hello, my name is Marisol Loza. This is my group and I's speed of light presentation. Original process, original lab equipment. During Galileo's 1930s time, the lab environment consisted of outdoor hilltops with lanterns during his lantern experiment. Lab equipment. During Galileo's observation, he used lab equipment like covered lanterns, assistance, and line of sight baseline to measure. Experimental procedures. Galileo tested light speed by stationing two observers on the distant hilltops, each with a covered lantern. Observer A uncovered their light. When B saw it, B immediately uncovered theirs, and A timed the round-trip response. He repeated the trial at different separations, hoping the delay would grow with distance. But human reaction time and crude clocks dwarf the microsecond travel time, so the test only showed that light's extremely fast, not its precise speed. Original difficulties. Some initial hurdles. Galileo's lantern test was thwarted by human reaction time and crude clocks, which couldn't resolve microsecond light travel. Manual shutters and dim, flickering lanterns added variable delays, while synchronization, line of sight, visibility, and uncertain distance measurements further masked any true signal. Safety issues. Nighttime hilltop work with open flame lanterns risk falls, burns, fire, smoke, fume, and exposure. Glare-induced vision loss and weather-driven disorientation, made worse by fatigue and poor communication. Equipment issues. Dim, flickering flame lanterns and laggy manual shutters made timing inconsistent. Unfocused beams, shaky alignment, and imprecise clocks serving added big uncertainties, killing repeatability over long distances. Information processing issues. Human limited timing and on synchronization clocks created big variable timestamp errors. Ambitious signals and sparse, noisy data led to big and poor statics, making a microsecond light time signal essentially unrecoverable. Original motivation. Original goals of the sciences. Galileo's original goal was to test whether light travels instantaneously at an infinite time, and if finite, to estimate it by detecting a measuring time delay between sending a lantern flash from one hilltop receiving the return flash from another. This discovery was intentional. Galileo deliberately designed the lantern test described in his 1638 Two New Sciences to check whether light's propagation is instantaneous or infinite by timing a send and return signal between hilltops. Who is expected to benefit? Primarily natural philosophers and astronomers, clarifying whether light has an infinite speed would advance fundamental physics and observational astronomy. Some immediate benefits. It clarified that light speed is measurable quantity and is set a particular lower bound on cc, highlighting the need for better instruments. That negative result directly inspired later, more precise methods. Some immediate advancements in the original field. It pushed optics toward quantitative timing, treating cc as measurable, emphasizing long baselines and precise clocks, exposing the limits of lanterns, shutters, and human reaction time, directly motivating brighter sources, better culmination, and improved timing instruments. Immediate advancements in other fields. It boosted precise timing and long baseline thinking beyond optics, nudging astronomy and horology. Immediate advancements in brand new fields. None sprang up immediately. Galileo didn't birth new fields on the spot, but it seeded several that matured later, such as psychophysics, human factors, treating reaction time and perception limits as measurable valuables. The modern process. Modern lab environment. A modern lab uses dark, vibration, isolated optics room with lasers, fast photodiodes, and pro-second timing, precision baselines, and environmental sensors to measure time of flight or cavity ring down. Modern lab equipment. Laser eyewear, interlocks, beam enclosures, warning indicators, fire extinguishers, ESD mats for photonics. Modern and experimental procedure. Modern lantern tests use two stations with fast LEDs and photodiodes. A flashes, B auto flashes back on detection. A times the round trip with microsecond, nanosecond electronics, subtracting known electronic delays. If no delays rises above timing noise, report a lower bound on CC, which faster timing or longer baselines. You can resolve the microsecond/ns flight time directly. Modern differences. Some modern advancements. Modern versions replace flames in human reaction with fast LEDs, nanosecond timers, and GPS synced clocks, plus proper optics and shielding, so they're safer, cleaner, and can actually resolve the round trip light delay. Modern protection. LEDs, class 1 and 2 lasers only, eyewear, enclosed beams with dumps, stable mounts, cable management radios, clear LOS, weather abort rules, fit first air kit, and pre-run checklists. Modern information gathering, timestamp flashes with GPS / RB synced photo data, log raw waveforms in Lantern-C, record distance, then fit delays, correct for index, and report CC with an uncertainty budget. Modern information processing. Modern systems use photodiodes and microcontrollers or GPS synthesized timers to record flash and receive times automatically. Modern benefits. So modern benefits of the research. Modern light speed research drives advancements in timing, optics, data handling, and standards that power much of today's communication. Navigation, scientific measurements, technologies. Other fields that benefit from the research. The same precision timing and optic measurement methods born from studying light speed now power advances in space, communication, navigation, health, and quantum technology. Examples of technology spawned is fiber optic communication. High-speed internet and global data networks depend on precisely known light propagation in fibers. Laser rangefinding and LIDAR, use in mapping, self-driving cars, surveying, and environmental sensing. Some future expectations. Future goals for scientists. Future goals aim to push for the limits of precision, communication, and understanding of space-time using ever better control and measurement of light. Potential benefits to come. Future benefits include safer communication, smarter navigation, faster computing, sharper imaging, and deeper understanding of the universe.
So for original process, the original lab environment was it had to be an open room. They couldn't have a lot of interference with the light. And then for equipment, they had to have light. They had used a wheel and a motor. And then for original experiment procedures, they shined the light and saw it reflect from the mirror. And then for original difficulties, an initial hurdle was to determine the wheel's rotation speed. For safety issues and equipment issues, the wheel could shatter, and then because light was getting shined through such small and it was light, it could hurt eyes because of the intense light. And then for information processing issues, limitations of visual observation. Original motivation, the original goal was to measure the speed of light. And then who was expected to benefit? Physicists were expected to benefit for having the first non-astronomical measurement of the speed of light. And original benefit, immediate benefit and advantages was the first precise way to measure the speed of light through air on Earth. And for modern process, again, you need an open area to measure the speed of light. And then for lab equipment, you needed light, mirrors, a motor, and an eyepiece. And then the experiment process, your procedure was to shine light through the rotating mirror and watch and see how the light reflected back. Modern differences. Modern advantages. Experiment did not take up as much space, and it could be measured through more than just light, or through more than air. Modern protection and safety. The wheel was no longer used, so they didn't have to worry about it shattering, and the motor was safer. Modern information gathering processing measured how long it took the light to get to the mirror. For modern benefits of research created an accurate way to measure the speed of light in air and in water. Other fields that benefited. The field of physics and astronomy benefited. Technology spawned. It led to the invention of the gyroscope. And then future expectations. Future goals for scientists. Understanding the speed of light helped physics and astronomy. After 1983, scientists are certain that they have the exact measurement for the speed of light, so it is no longer measured. Like, just the speed of light is no longer measured. And then for potential benefits to come, since they know how to measure the speed of light exactly, they can have technology working faster.
For my original process, I picked the Fizeau experiment carried out by Hippolyte Fizeau. He had a reflection device between two hills outside of Paris, France, called an interferometer. He would record the speed of light reflection in water using mirrors. The initial hurdles that he had was setting up the angles for the reflections from such long distances between the hills. And then the safety and equipment issues were accounting for different distances and changing temperatures that may affect the speed of light. And his information gathering issues was having to work against pre-existing formulas that determined how water affected speed. The original goal was to account for how fast light travels while in water to get a better overall measurement of its speed, and the science community was expected to benefit as it would be a huge step forward from previous formulas that were. The immediate benefits and advantages proved that water affected the speed of light and forced scientists to accept a medium moving through the stationary aether drives light. For my modern lab experiment, I used the Michelson-Morley experiment. It was held outdoors at the U.S. Naval Academy at Annapolis. The lab equipment was a Michelson interferometer, which is a modernized version of what the Fizeau used in his experiment. The modern experiment was using a modernized interferometer to determine the interference of aether and Earth fringe shifts in the measurement of the speed of light. The initial hurdles and equipment issues were having to invest in and build a modernized design of an older device that measured light being altered by aether rather than water. And the information processing issue was that he was later told by other scientists that the expected fringe shift should be 0.02 rather than 0.04 as he had originally measured it, and the experiment had to be redone 6 years later in 1887. One of the modern advancements were that interferometry became more honed in as a device with modern attachments. Modern protection and safety was that there were all in place at the time than the Fizeau experiments. The advantage was that cavity resonance provides better and more intricate science to gather information. Some of the modern benefits include that broader fields of sciences can come together, share, and test differing theories and information. The other fields that benefit from the research include astrology and cosmology, and examples of technology that spawned were GPS, laser, radar, and cutting-edge optical computing. Some of the future goals is to better understand and test relativity and to advance space exploration and other technologies. Some potential benefits is a better understanding and deeper knowledge of the world.
The original lab environment involved early astronomy towers with large windows and stable telescope mounts to ensure consistent measurements under nighttime observations. Some of the original lab equipment was refracting telescopes, mechanical clocks, observation tables, and notebooks. In 1676, Roemer would observe Lo's eclipse, which would disappear behind Jupiter every 42.5 hours. Roemer concluded that every time Earth moved away from Jupiter, Lo's eclipse would appear delayed, resulting in the fact that the light takes time to travel to Earth. With the known width of Earth's orbit, he was able to estimate how fast light must travel. Some of the initial hurdles: the speed of light was only a theory at times, and Roemer would have to convince other scientists that the theory was correct. Some of the safety issues was prolonged observation times in cold environments at night, risk of falls as telescopes were often placed at rooftops in the dark places, some equipment issues, weather, telescope precision, non-accurate mechanical clocks were all a part of equipment issues, some processing issues, manual calculations caused human errors, and data was handwritten, making it easy to be lost or misread. Roemer's goal was to improve the prediction of Lo's eclipse, not to measure the speed of light. This discovery made it partially intentional, as Roemer observed that the eclipse timings depended on Earth's distance from Jupiter. Who was expected to benefit from it? Astronomers, navigators, explorers, and the growing scientific community. Roemer's discovery showed that the speed of light takes time to travel, which revolutionized scientific understanding and enabled astronomers to use new methods for solar system motion predictions and measurements. Some of the immediate advancements in the original field in astronomy: Roemer's discovery led to creating more accurate predictions of Jupiter's moon's orbit, also gave evidence that Earth revolved around the sun. In other fields, Roemer's discovery led to safer sea navigations and for better map making. In relativity, Roemer's results led to Einstein proving that the speed of light is a constant. In the modern process, the modern lab environment includes a dark laser laboratory with controlled temperature and an optical bench which allows for the light beam to stay steady and precise. Some of the modern lab equipment includes pulsed laser beams, high-speed photo detectors. Modern experimental procedures include a time-of-flight experiment, which involves sending laser pulses through a measured path, which could be an optical fiber or across the laboratory before returning. Pulse is measured with an oscilloscope to determine the light speed through distance divided by time calculations. Some of the modern advancements: scientists achieve better light speed measurements through their implementation of high-precision lasers and digital timing tools which operate at picosecond, trillionth of a second time intervals. Some of the modern safety issues are the high-power laser light exposure. It becomes dangerous, so laser labs implement protective eyewear and beam enclosures and warning signs and interlock systems. The recording process of a computer system uses photodetectors and oscilloscopes to automatically measure data, which produces thousands of pointers per second for better measurements and accuracy. Some of the modern information processing: the recorded data undergoes software analysis to perform results, averaging and error removal and noise reduction before executing the speed of light calculations using precise mathematical formulas and uncertainty evaluation methods. Some of the modern benefits of the research strengthened engineering, science, and technology with the improvement of time and distance standards to extreme accuracy. Benefits in other fields such as medicine with laser surgery and medical imaging, aerospace with spacecraft communication timing, communications with high-speed data transfers. Some of the technology spawned is LiDAR, fiber optic, internet, and laser technology, and the picture shows LiDAR, which is used to this day for cars such as Teslas. Some of the future goals are study light in extreme conditions. Scientists conduct experiments to study light behaviors near black holes and neutron stars in quantum vacuum environments. Another goal would be faster communication. Scientists actively develop faster and more secure fiber optic and quantum communication systems through advancements in light. Some of the potential benefits are new insights into black holes, dark matter, and fast quantum computers.